Now, before performing another true volume integral, but this time using spherical coordinates, this is an intermediate little exercise which helps us to understand why this, let's call it a magical factor, the so-called Jacobian, why this always has to be considered and how it comes about in detail. Well, this is really, you could say, quite an interesting but also a little complicated procedure, because if you perform a coordinate transformation, you always have to consider that the matrix of your whole new system of coordinates is a totally different one from the one before, especially the matrix for Cartesian coordinates, which we call the Euclidean matrix, is quite simple. It just it's sufficient for a volume element, you know, like dv to multiply differentials of the three Cartesian coordinates. But using spherical coordinates, it's not so simple anymore. Let alone the fact that two of these variables aren't even distance variables. Instead, they are angular variables or coordinates. And so there is not even a right angle between, you could say, the directions you're moving along when building a differential volume. Well, that's not so easy. But things even get more complicated if you mix up the two different common ways of defining spherical coordinates, which we discussed outside of this session, right? So I'm using this definition of spherical coordinates, which is very analogous to the geographical coordinate system, where you could say the phi angle is, it is quite truly, it is a horizontal angle, much the same as in the other definition of spherical coordinates, and the theta is a vertical angle. Also, this is the same in the other way of setting up spherical coordinates, but there's a certain difference in the way defining this vertical angle of theta. So what I'm doing definitely is importantly to say that theta runs from negative pi half on the negative z-axis up to positive pi half on the positive z-axis, which means it's like in geographics, it's the vertical angle measured from the south pole over the equator up to the North Pole. So that's what it is, okay? And if I do so, it turns out that these are the exact, well, you could say this is the system of equations for the back transformation from spherical coordinates given to Cartesian coordinates resulting. That's what you know, but also, you know, in the lecture, it has been used, the other definition, which means that here you have a sine of theta, here you have a sine of theta, and here you would have a cosine of theta, which also means that theta runs from 0 to 2 pi. That's important. And then the Jacobian factor, which we just try to find out, will be a little different. We'll see at the end. Now, let's start. And as you all know, because we don't want to derive this here, we just want to use it, namely the fact that the Jacobian matrix is set up in a certain way, which you see here. First of all, this is the radius vector function for any point in space expressed in spherical coordinates. So this is the whole thing given as in vector notation. So then we just want to calculate the determinant of the Jacobian matrix, which is set up to be the first of the old coordinates, well, partially differentiated for one after the other of the new variables. I decide to use the order of R, U, V. Now, please know that I'm using U and V for a little simplicity of writing instead of phi and theta. Please allow me to do so. And then afterwards, we will do a replacement back. So just remember for a while, U is the same as phi and V is the same as theta. I'm quite, well, I don't know, it's in certain contexts, it's it's like a standard to use u and v as we have done before as the variables, for example, for curved surfaces and so on. And if I keep r constant in this case, I would have my uv function of the surface of a sphere. So that's the reason why. But anyway, we have to make sure that there is a fixed order of the new variables also, which is now r phi theta or r u v. Also, this is it's important. This is a right-handed system in this way, which I might show you using a little sketch of the sphere, but we don't have the time for this now. So this is given. It also leads to a normal vector mathematically, which points outwards of a sphere. Okay, so that's why this is the order that we use. Now, just technically, what is this is the first row of the Jacobian. Second row, much the same, but referring to or starting with the second of the old coordinates, and the third row takes the third one, and always take the partial derivative with respect to one of the new coordinates, one after the other. So this one differentiated for r, easily we consider u and v to be constants. So we have a linear term, and r gets differentiated away. Cosine of u times cosine of v stays there. So that's quite simple. But then, second step, differentiating for u, we keep r times cosine of v as constants, constant factors, stay there. Cosine of u gets differentiated to negative sine of u. So negative drawn outside. Also, that's done. And then x partial derivative for v this time. Well, r times cosine of u, we don't touch it, we just leave it alone. And then cosine of v differentiated for v gets negative sine of v. Please note, in both cases we have a minus sign, but different terms of u and v, not to be mixed up, please. You see, sine and cosine, cosine and sine. It looks similar, but it's different. Now, second row, analogously, in the first step, the r factor goes away. Sine of u times cosine of v stays there. Now, secondly, partial derivative for u. Sine of u has a derivative which is cosine of u. The other factors, r times cosine of v, stay there. Third step, take the partial derivative for v, so y index v, and this time we get cosine of v differentiated to the negative sine of v again, but this time r times sine of u stays there. So even this is different from this one. In the third row, we have much more simply, because u does not appear, we have the term r times sine of v for the z component. Remember, in the lecture, it was r times cosine of v or of theta instead. Now, differentiating for r, we get sine of v. Differentiating for u, we get nothing, or we get 0, because it does not depend on u. You know, this is a constant then. You could say an additive constant, which just disappears. I just underline this for special reason, you see shortly. And then the third step, z for v, we get sine of v differentiated to be cosine of v, and factor of r stays there. So the third row is obviously the most simple, and that's why, in order to get the determinant done, it's a good idea to decide expanding this whole determinant along the third row. You remember this method, right? So because the main reason is I got a 0 inside here, which means in the second step I will just have a 0 term, which means I have less effort in the end. So that's an advantage, clearly. Let's just remember we have this chessboard-like scheme of signs, okay? Scheme of signs, of mathematical signs, which always is the same in a quadratic matrix. It starts with the positive and then goes to negative, to positive, all the way. It's quite simple, okay? So we get plus, minus, plus, minus, plus, minus, plus, minus, plus. And we're referring to the third row where the signs, corresponding signs are positive, negative, positive. This one doesn't have to be regarded because it refers to the zero. So we have positive and positive for both these contributions. Let's just start. We take the sign of V and multiply it with the determinant of the submatrix. You remember, we then in the next step we would just cross out this cross out this row and cross out this column, and what remains gets to be our submatrix, and its determinant may easily be calculated by diagonal product minus second diagonal product, as you all know. So that's what I'm doing, and I get this, what you see here. You just believe me. In the second step, I take the r times cosine of V and then cross out. This is what, yeah, you see, this is what remains, the second submatrix we have to consider. So carefully take these terms over and look what you get. And you will see that, well, it looks complicated for a while. Sine of V, look here, I take this term multiplied with this term. First of all, the negative sign gets away, it disappears. When I get r times r, this is r squared. I have sine of u and again sine of u, so sine squared of u, but I have the cosine of v and here the sine of v. So the product of sine of v times cosine of v, just resort it. Plus, but why is it a plus? Well, we have to subtract the second diagonal product. And since here's a minus, and I say minus this times this, it gets positive again. We get a positive sign, plus, but then again also r times r is r squared, cosine of u, this cosine squared of u, and then sine of v times cosine of v. That's interesting. If I underline the sine squared and the cosine squared in blue color, I see that the remaining factors here and here are the same. It's nice because it means that I can put this sum of squared sine and cosine of u in parentheses as always, as often, and then state that this factor equals 1. You know it, the famous fundamental equation of sine and cosine, which states that squared sum of sine and cosine always is 1. So that simplifies quite a lot. Let's look at the second contribution, r times cosine of v. Then again, we take diagonal product minus second diagonal product, other way around, this one, diagonal product minus second diagonal product. So we have r, this time we only have one factor of r, you see here, but we also have cosine u times cosine u, cosine squared of u, again, as before here. Then we have the cosine of v and again the cosine of v, so this time it's cosine squared of v, plus then subtracting this product, you see again, minus times minus gets plus. So we have a factor of r, and we have sine of u, sine squared of u times cosine squared of v. This time, we should underline the cosine squared of u here and the sine squared of u here. Again, the remaining factors r times cosine squared of v are the same here and here. So it's quite similar, this simplifies. And that's what I do in the next step. Then also, well, just look what I'm doing. I get sine of v, don't look at the pink color here, sine of v times, and all that remains here is r squared times sine of v times cosine of v after putting the blue, you know, the squared sum in parentheses. That's it. And then in the second contribution, where am I? Let me see. So that's what it was. Sorry, I lost my focus. Yeah, that's what remained from above, from here. This one and here the same. So that's all that remains from the first row. Now the second row. Here, plus r times cosine of v, and this simplifies to be r times cosine squared of v. So that's what we can see. Okay, by you could say that the bluely and well, violetly underlined terms disappear while the others are fusioned. Okay, so that's it. But now here I have a sine of v times sine of v. And here I have already my cosine squared of v. So if I put these two together, this is again sine squared of v, this is a cosine squared of v, and the remaining factors are r squared, look here, times cosine of v, and here r times cosine of v times r, which is also r squared times cosine of v. So a third time I can put a certain squared sum of sine and cosine in parentheses, and what remains is the additional factor once, which now in the end is r squared times cosine of v. And that's a nice result, replacing back again, okay, u against phi and v against theta, we get r squared times cosine of theta. And Evgenia and everybody, now you see, if I'm doing everything correctly in this way of, in this version of spherical coordinates, I get correctly this Jacobian factor, which tells me how to transform a volume element from, well, you could say from spherical to Cartesian coordinates. So the end result is that a differential volume element, which is regularly the product of the Cartesian differentials, equals, at least in the limit, as you know, this is a differential statement, equals the product of the spherical coordinates, but with an additional correction factor of r squared times cosine of theta. And if you use the different version of spherical coordinates, at this place you have r squared times sine of theta instead. So, and now for you to know, because what I've been using last session already is this Jacobian factor, but not to the purpose of calculating a volume integral, sort of, and I did not need this whole differential expression. Instead, I was setting r equal to capital R, which is constant, and it means that we just move along a fixed, the surface of a certain sphere around the origin. Okay, so that's just the reduction for one variable. And it means in the end that a surface element on the curved surface of a sphere equals still the same Jacobian factor, but then times, well, I called it du, dv, or you can even use d phi times d theta, it doesn't matter, on the spherical surface. But the reason that the Jacobian factor stays the same is a special one. The reason is that exactly the radius variable is the one that does not need any correction. And if we set this to be constant, so that its differential disappears, we don't take anything away from this correction factor. So actually, this correction factor geometrically, refers to as well to the phi as to the theta contribution. More in detail, I can tell you that the correction for the differential theta is just a factor of r, while the correction for the phi differential is the remaining factor of r times cosine of theta. So that's how this, that's the interesting way how this Jacobian, which we calculate purely algebraically, is to be explained in a geometrical manner. What's its function? And it shows, it turns out that there's no influence on the r increment, because this is just a regular distance variable. There is much correction for the phi, as I told you, r times cosine of theta, and there's a little correction for the theta, which is just a factor of r. So you can see this in a way in this sketch here, if you just try and think yourself inside of this. So, and for clarity, I had to replace this angle of theta, I had to rename it, I hope you can recognize it, to be theta tilde. I just used this tilde symbol above, so that you don't mix it up with my theta, because now that's the relation. This theta tilde, okay, I have to use the tilde here also, is the one that runs from the positive z-axis with a value of defined to be 0 there. It runs downwards to the negative z-axis in a range from 0 to 2 pi. That's what Martin Ebert used also in the lecture, right? And now, but the only difference is that's the connection. This kind of theta tilde, equals pi half minus the other kind of theta. You see, if this theta runs from negative pi half to positive pi half, you insert here, you find your theta tilde running from 0 to 2 pi. That's it. And then also by this relation between the two, the cosine of one of them is the sine of the other one, and the sine of this one is the cosine of the other one. So this just exchanges. It means in the end, this is a geometrical explanation why the differential area on a curved spherical surface has a correction factor, or a geometrically visible a factor of r squared times sine of this theta tilde angle here in our nomenclature, in our way of naming it, it's r squared times cosine of theta. But where does it come from? Try and see it. If I go from here to here, there you see that since the differential phi is just, well, it's an angle in radians units, but it has to be multiplied with its distance here, in this case from the z-axis, which and that's complicated because this is a contribution of capital R, radius of the sphere, times sine of the theta angle, which is measured from here to there. And also, I hope you can see this right triangle here, where the right angle is there, but don't mix it up with this phi measured from the positive x-axis counterclockwise, okay, around the z-axis. Here you can see the theta tilde. And so for the same, or for a similar reason, the correction for an increment of theta, no matter whether it's taken to be this or that, is just a factor of r, because this refers to the origin, distance from the origin. And that's the factor of r, part of the Jacobian, right? Acting on differential theta, and a factor of r sine of theta, or theta tilde, acting on a differential of phi. And all together, these make up the r squared times sine or cosine of theta contribution here, on correction factor. Even when I put when a differential radial increment comes into play, and I describe whole differential volumes. So it's interesting, a little bit confusion, sadly, due to the different theta definitions, but it's interesting to see how the geometrical derivation of the Jacobian also works. That's what I wanted to add.